There is a planet out there that breaks the rules, not in a metaphorical way, not in the way scientists sometimes say something is surprising when they really mean it gently deviated from their expectations. We're not talking about a minor anomaly that gets filed away and forgotten. We're talking about something that, when astronomers first processed its data, forced them to double-check their instruments, rerun their calculations, and quietly ask themselves whether they had made a mistake somewhere. Because the numbers they were seeing were, by almost every framework of planetary science we had built up over decades, impossible. Think about what a planet is supposed to be. When you imagine a planet, any planet, there is an implicit assumption buried in that image. Planets are objects made of stuff, rock, gas, ice, metal. Whatever combination you choose, whatever world you picture, planets are dense enough to hold their shape under gravity. They have presence. They have substance. When we look at the worlds in our own solar system, even the lightest among them, Saturn, the planet so famously buoyant it would theoretically float on a sufficiently vast ocean, still has enough material in it to crush you long before you found its core. Even Saturn, the cosmic lightweight of our neighbourhood, has a density of about 0.69 grams per cubic centimetre. That is less than water. That is genuinely strange, and we have spent decades trying to understand why Saturn is as light as it is. Now imagine something almost 12 times lighter than Saturn. Not 12% lighter, not a little lighter, or noticeably lighter, or significantly lighter. 12 times, lighter by an entire order of magnitude. A world so improbably, almost offensively diffused that the material making it up has roughly the same average density as spun sugar, as cotton candy, as the airy nothing you pull off a paper cone at a carnival and watch dissolve on your tongue in seconds. That is what astronomers found. That is what is orbiting a distant star, approximately 1,200 light-years from Earth, completing a full circuit of its sun every 6¼ days, swelling through the void of space as one of the most physically inexplicable objects ever confirmed to exist. And here is the part that makes this stranger still. This is not a small planet. This is not some microscopic oddity that we can explain away as a dust cloud or a remnant of a collision or some temporary configuration of gas that will collapse into something normal eventually. This planet is enormous. It is larger than Jupiter. In terms of pure physical size, in terms of how much space this object takes up in 3 dimensions, it is among the biggest kinds of worlds we know of. Jupiter, the titan of our solar system, the planet so massive that all other planets in our solar system could fit inside it with room to spare, this world rivals that. Exceeds it, in fact, in raw volume, and yet it is almost weightless. A planet the size of Jupiter that has, by the most precise measurements we can make from here, roughly the mass of a marshmallow, relatively speaking. A planet so light that if you could somehow extract just the gravitational field from Jupiter and transplant it into this world, you would have packed more than 9 times the mass into the same container. If you stood on the hypothetical surface of this planet, though surface is a complicated concept here, and we will get to that, you would weigh almost nothing. The gravity pulling you down would be so faint, so tentative, so barely there, that you might wonder if the universe had forgotten to include it at its proper strength. How does something like this exist? How does a planet get this big and stay this light? What is inside it? Or more accurately, is what is not inside it? What is holding it together? What keeps it from simply drifting apart into the emptiness around it? These are not rhetorical questions. These are the actual questions that real astronomers, working with real data, with decades of combined expertise in planetary physics, have been grappling with since this planet came to their attention. And the honest answer, as of right now, is that they do not fully know. This is the story of WASP-193b. It is a story about an object in space that challenges almost everything we thought we understood about how planets form, how they grow, how they hold themselves together, and how strange the universe is still capable of being when we look far enough out into it. It is a story that begins with a telescope watching a star, a tiny dimming of light, and a measurement that made astronomers stop and look at each other, and it expands into one of the most fascinating unsolved problems in modern planetary science. But before we can truly understand why WASP-193b is so extraordinary, we need to understand something more fundamental. We need to understand what density means in the context of planets. We need to understand why it matters, deeply, fundamentally, structurally, and why a number that seems abstract on the page translates into something genuinely mind-bending when you consider what it implies for a world this size. Because the strangeness of WASP-193b is not just a curiosity. It is a crack in the wall of our understanding. And through that crack we can see how much we still do not know. Let us talk about density. Not in the way a textbook talks about it, as mass divided by volume, a ratio, a formula. Let us talk about it the way the universe uses it, as a kind of fingerprint. Because density, more than almost any other single measurement we can make about a distant world, tells us what kind of thing we're looking at. It tells us what a planet is made of, where it formed, how it evolved, whether it is solid or gaseous, ancient or young, stable or actively transforming. Density is not just a number, it is a story compressed into a ratio. Start with the rocks. The terrestrial planets, Mercury, Venus, Earth, Mars, are dense by planetary standards. Earth sits at about 5.5 grams per cubic centimetre. Mercury, despite being small, is similarly dense at around 5.4. These numbers tell you immediately that you are dealing with iron, silicate rock, compressed minerals, solid worlds, worlds with iron cores and rocky mantles. When you see a density like that, you know what you're looking at. Something that formed close to its star, in a region where temperatures were too hot for ices and light gases to condense, where only heavy materials could survive. Then come the gas giants, and density drops dramatically. Jupiter, the largest planet in our solar system, has a density of about 1.33 grams per cubic centimetre. That is still denser than water, but only barely. It tells you this is a massive hydrogen and helium world, but one with a significant core, probably rock and ice and metals compressed by enormous gravitational pressure deep beneath thousands of kilometres of gas. When you put Jupiter's mass and volume together and get 1.33, you are looking at a planet where the gas itself is being compressed by its own weight into something almost fluid, something with physics more exotic than anything we encounter on Earth. Saturn, the runt of the gas giant pair in terms of density, sits at 0.69, below water. The reason Saturn is less dense than Jupiter, despite being almost as large, has to do with a complex interplay of mass and internal structure. Saturn is not massive enough to compress its gases as thoroughly as Jupiter does, so its interior is somewhat more spread out. The famous fact that Saturn would float in an ocean large enough to hold it is not a metaphor. It is literally true. A consequence of that number, 0.69, the ice giants push density back up somewhat. Neptune clocks in at 1.64, Uranus at 1.27, both denser than Jupiter because they are made of a heavier ices, water ice, methane ice, ammonia, beneath their gaseous envelopes. This material is heavier than pure hydrogen and helium, so even though these planets are smaller than Jupiter, they pack more mass per unit volume. What this survey of our solar system teaches us is that density is a direct window into composition. High density means rocks and metals. Intermediate density means ices and heavy molecules. Low density means hydrogen and helium. Very low density means a hydrogen-helium envelope that is somehow spread out further than it should be. An extremely low density, lower than anything in our solar system, means something we have not fully figured out yet. The boundary at which density becomes deeply puzzling in an exoplanet is somewhere around 0.1 grams per cubic centimetre. At that point, you are looking at a world so inflated, so unreasonably puffed out, that standard models of planetary structure and evolution struggle to explain it. Astronomers have a name for this category: superpuffs. They're planets with impossibly low densities, bodies that seem to have been inflated far beyond what their mass and their distance from their star should allow. WASP-193b has a density of approximately 0.059 grams per cubic centimetre. Let that number settle for a moment. 0.059, not just below 0.1, not just in the superpuff territory. More than 12 times less dense than Saturn. About 17 times less dense than water, in the range of cotton candy, which has a density of roughly 0.05 grams per cubic centimetre, depending on how it is spun. To call this unusual is an almost comical understatement. Saturn is unusual by solar system standards. WASP-193b is unusual by a factor of 12 compared to Saturn. In the entire catalogue of confirmed exoplanets, a catalogue that now numbers in the thousands, spanning an extraordinary range of compositions, sizes, masses and orbits. WASP-193b sits at the very edge of what has ever been measured. It is one of the least dense transiting exoplanets ever confirmed, and the word transiting matters here because it points to exactly how we found it. Finding planets around distant stars is not easy. For most of human history it was impossible. Stars are so far away that even the largest planets orbiting them cannot be seen directly. The light from the star overwhelms anything reflected from a small dark companion. For centuries, we knew intellectually that other stars probably had planets, but we had no way to prove it. That changed, slowly and then rapidly, over the last few decades of the 20th century and the first decades of the 21st. Astronomers developed techniques of extraordinary cleverness to pull signals out of starlight that nobody had thought to look for before. The technique that found WASP-193b is called the transit method. It is elegant in its simplicity and remarkable in its sensitivity. When a planet orbits a star, and that orbit happens to be aligned such that the planet passes between the star and our line of sight, something measurable happens. The planet blocks a tiny fraction of the star's light. For a few hours, the star appears very slightly dimmer, not to the naked eye. Not by any amount a human could detect without instruments, but measurable with sufficiently sensitive photometers. The amount of dimming depends on how big the planet is relative to the star. A large planet crossing a small star might block a few % of the light. A small planet crossing a large star might block only a fraction of a %. This dimming, called a transit, repeats every time the planet completes an orbit. If you watch a star long enough and you see a regular pattern of these miniature dimmings occurring at precise intervals, you have almost certainly found a planet. The interval between transits tells you the orbital period, how long the planet's year is. The depth of the dimming, how much light is blocked, tells you the planet's size relative to its star. If you know the star's size from other measurements, you can calculate the planet's actual radius. This is the foundation, but it is also, critically, a measurement of size only. Transit photometry tells you how big a planet is. It does not tell you how massive it is. And here is where the strangeness of WASP-193b begins to reveal itself. Because mass and size are supposed to be connected, and the relationship between them is what makes WASP-193b so disturbing. To understand the mass, you need a second technique. The technique for measuring the mass of an exoplanet from Earth is called radial velocity, and it is, when you stop to think about how it works, one of the most quietly brilliant pieces of physics in practice that astronomers have ever developed. Here is the idea. When we say a planet orbits a star, that is technically not quite right. What actually happens is that both the planet and the star orbit their common centre of mass, a point between them that depends on their relative masses. For a very massive planet orbiting a much less massive star, that centre of mass might be somewhere outside the star's surface. For a small planet orbiting a huge star, the centre of mass is deep inside the star, essentially at the star's own centre. But in all cases, the star is not perfectly still. It wobbles slightly, guess in response to the gravitational tug of its planet. As the planet pulls the star in one direction during part of its orbit, and in the other direction later, the star rocks back and forth very slightly. This motion is tiny. For a planet the size of Earth orbiting a star the size of the Sun, the induced stellar wobble is only about a few meters per second. For a heavier planet, the wobble is larger. Now, if the star is wobbling toward us and then away from us as seen from Earth, this motion has a measurable effect on its light. When the star is moving toward us, the light waves are compressed very slightly, shifting the star's spectrum toward the blue end. When the star is moving away, the light is stretched slightly toward the red. This is the Doppler effect applied to starlight. The amount of spectral shifting, the amplitude of what astronomers call the radial velocity signal, is directly related to the mass of the planet causing the wobble. Together, transit photometry and radial velocity give you a planet's size and its mass. And from size and mass you can calculate density. The density is the thing that tells you what kind of planet you are dealing with. For WASP-193b, when astronomers carried out this full measurement campaign, what they found was that the transit signal was consistent with a planet substantially larger than Jupiter. A genuine giant, a genuinely massive seeming object in terms of physical extent. So far, this was unusual but not unprecedented. There are hot Jupiters, close-orbiting giant planets that have inflated radii. They tend to run large because of the intense stellar heating they receive. But then came the radial velocity measurements, and this is where the situation became deeply strange. The radial velocity signal, the stellar wobble induced by WASP-193b, was small, much smaller than you would expect for a planet this large. Embarrassingly small in a sense given the size implied by the transit. When the numbers were combined, when the radius from the transit and the mass from the radial velocity were put together and the density was calculated, the result was roughly 0.059 grams per cubic centimetre. This was not what anyone expected. This was not a slightly inflated giant, a mildly unusual hot Jupiter that could be explained by standard irradiation models. This was something entirely different. The planet was enormous, comparable in volume to the biggest gas giants we know, but it had barely any mass. It was, for its size, almost nothing. This is the measurement that made astronomers pause. Not because they doubted their instruments. The observations were repeated, checked, confirmed by multiple facilities, but because the result was so far outside ordinary expectations that it demanded explanation. What was this planet made of? How had it formed? How was it holding together? Why, given that it sits so close to a hot star and has such feeble gravity, had it not already lost most of its atmosphere to space? And then, underneath all of these technical questions, an older and simpler question: what is this thing really? Before we can properly appreciate the planet, we should know something about the star it orbits. Because a planet is not an independent thing, it is always a product of its environment, shaped by its sun, defined by its relationship to the energy pouring down on it every second of every year. And the star WASP-193b orbits is, in its own way, an important part of the story. WASP-193, the star, is what astronomers classify as an F-type star. This puts it in a category slightly hotter, slightly larger, and slightly more luminous than our own Sun. The Sun is a G-type star, sitting in the middle of the stellar classification sequence. F-type stars are one step up. They burn hotter, they burn brighter, and they burn through their hydrogen fuel somewhat more quickly as a result. The difference in surface temperature between an F-type star and our Sun is not dramatic in absolute terms. We're talking about a few hundred to perhaps 1,000 Kelvin, above the Sun's approximately 5,780 Kelvin surface temperature. But in terms of the energy output directed at any planet in the system, it matters. F-type stars pour more radiation into their environments. They are more intense light sources, and for a planet sitting as close to one as WASP-193b sites, that intensity is something you cannot ignore. WASP-193b orbits its star at an extraordinarily close distance. Its orbital period is approximately 6.25 days. For comparison, Mercury, the innermost planet in our solar system, a world that we consider definitively too hot and too close to its sun to possibly be habitable, takes 88 days to complete an orbit. WASP-193b completes its circuit in 6.25 days. It sits roughly 80 times closer to its star than the Earth sits to the Sun, give or take. It is scorchingly, devastatingly close. This means WASP-193b is what astronomers call a hot Jupiter, or more precisely, it belongs to the broader category of short-period giant planets, worlds of Jupiter-like size or larger that orbit so tightly around their stars that they were, until the mid-1990s, widely believed to be impossible. The existence of hot Jupiters was itself one of the first great surprises of exoplanet science, because nothing in the standard model of planetary formation predicted that giant planets should form or survive so close to their parent stars. Their discovery forced a complete rethinking of how planets migrate and evolve over time. But while ordinary hot Jupiters are now reasonably well understood, or at least we have working frameworks for how they get where they are, WASP-193b sits in a different class entirely. Its proximity to its star is one of the inputs to its strangeness, but proximity alone cannot explain the degree to which it defies expectations. There are many hot Jupiters, Most of them, even the inflated ones, have densities orders of magnitude higher than WASP-193b. This planet orbits in a regime of intense radiation and achieves a density that should not survive in that regime. It is simultaneously receiving enormous amounts of energy that should drive its atmosphere away, and yet it is still there, still enormous, still improbably light. The star is important to the story, but the star is not the story. The planet is. WASP-193, the star, sits approximately 1,200 light-years away from us. A light-year, to give this number its proper weight, is the distance light travels in a year, moving at nearly 300,000 kilometers per second for a full year. 1 light-year is roughly 9.5 trillion kilometers. Multiply that by 1,200 and you have the distance separating us from this system. The light we observe from WASP-193 today left that star when the Roman Empire was still a recent memory on Earth. We are not looking at this system as it is now. We are looking at it as it was more than a millennium ago, which is a reminder that all of astronomy is, in a sense, archaeology, a reading of ancient light. The discovery of the system came through the WASP survey, the Wide-Angle Search for Planets, a long-running program that has found dozens of exoplanets by monitoring the brightness of hundreds of thousands of stars and looking for the characteristic dips that signal transiting planets. WASP is a ground-based survey using relatively small telescopes, which makes its discoveries all the more impressive. These are not behemoths of engineering. They're modestly sized instruments with wide fields of view, designed to scan large areas of sky rather than examine individual targets in great detail. Their power comes from patience, automation and breadth. When WASP flagged WASP-193 as a candidate host star, what it saw was a recurring dimming consistent with a planet the size of a large gas giant. The follow-up work, the radial velocity campaign, the detailed photometric analysis, the characterization of the host star's properties, was carried out by a team led by astronomer Khalid Barkawi and collaborators, work that resulted in the announcement of WASP-193b to the scientific community and to the world. The paper describing the discovery was published in Nature Astronomy in 2024, and its conclusions were immediately striking to anyone who read them. A planet around 1.46 times the radius of Jupiter, a mass of approximately 0.139 times that of Jupiter, a density of approximately 0.059 grams per cubic centimeter, one of the least dense transiting planets ever measured. These numbers went into the scientific literature, and they did not fit neatly into any existing theoretical box. They were real, they were confirmed, and they were, in the most productive scientific sense of the word, a problem. Let us sit with these numbers for a while, because the full strangeness of WASP-193b does not announce itself immediately. It accumulates. It sneaks up on you when you start running comparisons. WASP-193b has a radius approximately 1.46 times that of Jupiter. That means in terms of sheer physical extent, the distance from its centre to its outer atmosphere, it is nearly half again as large as the biggest planet in our solar system. If you placed it next to Jupiter, it would visibly tower over it. It is a genuinely enormous object. Volume scales as the cube of radius, so that 1.46 factor in radius translates to a volume roughly 3 times larger than Jupiter's. Now here comes the mass. WASP-193b has roughly 0.139 times Jupiter's mass, not 1.39, not even 0.39, 0.139, about 14% of Jupiter's mass. In absolute terms, we're somewhere in the range of 44 times Earth's mass, which sounds like a lot until you remember that Saturn is about 95 Earth masses and Jupiter is about 318. WASP-193b, this enormous Jupiter-exceeding sphere, contains less than half the mass of Saturn. Much less. Saturn, which is already the least dense planet in our solar system, has about 95 Earth masses. WASP-193b has about 44, but WASP-193b is bigger, 3 times larger by volume. Run the density calculation. Take the mass, divide by the volume, 0.059 grams per cubic centimetre. Now compare. Cotton candy, approximately 0.05 grams per cubic centimetre, depending on how it is prepared. Balsa wood, around 0.12. Aerogel, which is one of the least dense solid materials humans have ever manufactured, a material so light and transparent that it looks almost like frozen smoke, around 0.001 to 0.002 grams per cubic centimetre. WASP-193b is denser than aerogel. It is not literally nothing, but it is in the neighbourhood of materials we think of as fundamentally insubstantial. Saturn, 0.69 grams per cubic centimetre. That is 11 times denser than WASP-193b. Liquid water, 1.0 grams per cubic centimetre. 17 times denser than WASP-193b. If you could somehow deposit WASP-193b into an ocean of liquid water large enough to contain it, it would float. The same is true of Saturn, famously. But WASP-193b would not merely float, it would bob at the surface with almost nothing beneath the waterline. It would float the way a balloon floats, with most of its volume above the water. The analogy breaks down for various physical reasons, but the density mathematics is real. This planet is almost 17 times less dense than water, which means it would displace far less water than its volume suggests. For comparison, the density of Earth's atmosphere at sea level is about 0.0012 grams per cubic centimetre. WASP-193b is about 50 times denser than air at Earth's surface, but that puts it more in the category of atmospheric gas than of anything we normally think of as a solid body. The implication of this is deeply strange. When you say a planet has a density of 0.059, you're implicitly saying that the material making it up, whatever that material is packed together less tightly, on average, than the material in most planetary atmospheres. Not in deep, high-pressure planetary interiors, not in solid cores. The average density of the entire planet is comparable to that of diffuse gas. This tells us something profound about how WASP-193b is structured. It cannot have a large, dense core. If it had a significant rocky or metallic core, comparable to what we believe Jupiter or Saturn have, the average density would be pulled upward from whatever the gaseous layers contribute. The total density represents the blend of everything, core, interior, atmosphere, everything averaged together. For the total to be 0.059, the core, if it exists, must be either very small in mass terms, or the envelope of gas around it must be almost inconceivably vast and diffuse. This is where standard planetary models really start to struggle, because the standard story of gas giant formation begins with a core. The core accretion model, the dominant framework for how Jupiter-like planets form, posits that a solid rocky or icy core of roughly 10 to 20 Earth masses forms first through the accretion of solid materials. Once that core reaches a critical mass, it begins pulling in gas from the surrounding protoplanetary disk, and the gas envelope grows rapidly, eventually far outmassing the solid core. But the core is supposed to be there. It is supposed to anchor the planet. And for the planet's average density to sit at 0.059 grams per cubic centimetre, any core WASP-193b might possess must be contributing almost nothing to the overall density budget. Some astronomers have suggested that WASP-193b might have formed differently from the standard model, perhaps through a process called disk instability, in which a clump of gas in a protoplanetary disk becomes gravitationally unstable and collapses directly into a planet without first assembling a solid core. This mechanism tends to produce gas-rich worlds with minimal rocky interiors, which could in principle explain a very low density. But disk instability models have their own challenges when it comes to explaining all the properties of a system, and they do not on their own fully account for the extreme inflation we observe. The numbers point at something, but they do not yet point clearly enough at an explanation. And that is the core of the mystery. Not just that WASP-193b is strange, but that its strangeness does not resolve into a single clean answer. WASP-193b did not arrive in a vacuum. When astronomers first began cataloguing exoplanets in earnest during the 1990s and 2000s, they found many things they expected: rocky worlds, gas giants, ice giants, hot Jupiters. But they also found a scattering of objects that did not fit neatly. Planets with densities so low they seemed almost wrong. Worlds that pushed the boundaries of what planetary science predicted should exist. Over time, this collection of outliers acquired a name: superpuffs. The term is informal, perhaps too casual for the scientific literature, but it has stuck precisely because it captures something real. Superpuff planets are, more precisely, low-density giant or intermediate-mass planets, whose radii are much larger than models predict given their masses. They are the cotton candy cousins of the respectable and well-understood gas giants. They defy simple categorization, and different ones likely defy it for different reasons. Some of the most famous superpuff planets were found by the Kepler Space Telescope, NASA's transformative planet-hunting mission that observed more than 150,000 stars simultaneously for years and identified thousands of planetary candidates. Kepler gave us our first statistical picture of what exoplanets actually look like across the galaxy, and that picture included a significant population of planets with low densities that required explanation. Kepler 51 was one of the early superpuff systems to attract wide attention. The Kepler 51 system contains at least 3 planets, and 2 of them, Kepler 51b and Kepler 51d, have densities below 0.1 grams per cubic centimetre. Kepler 51b in particular has a density of only about 0.03 grams per cubic centimetre, even lower than WASP-193b's 0.059. But Kepler 51b is a substantially less massive and smaller object than WASP-193b. The comparison between different superpuffs is complex because size and mass interact in ways that make direct comparisons deceptive. Kepler 18d was another early example, a planet roughly 6 times the mass of Neptune with a density of only about 0.06 grams per cubic centimetre. HAT-P-67b a hot Jupiter with a density somewhere around 0.05, WASP-79b, another inflated hot Jupiter. The catalogue of suspiciously light exoplanets is not trivially small. It is not a handful of flukes that can be dismissed as measurement errors. It is a pattern, scattered across thousands of light-years of space, pointing at a category of worlds that our models did not predict and still do not fully explain. But within this family, WASP-193b stands out, not just for its low density, but for the combination of its size, its mass, its orbital characteristics, and the quality of the measurements confirming it. Many superpuffs have large uncertainties on their mass measurements, because the radial velocity signal from a light planet is small and noisy, and difficult to pin down precisely. The mass of WASP-193b, while challenging to measure, we will come back to this, was pinned down sufficiently to make its density calculation reliable. Nay, this is important. In science, a result is only as trustworthy as the quality of the data behind it. WASP-193b is not a borderline case, a planet that might fall out of the superpuff category once measurements are refined. Its density is genuinely, confirmedly extremely low, and this makes it not just an interesting data point but a scientific challenge, something that must be explained, not explained away. What, then, are the explanations that have been proposed? The first place astronomers look when they encounter an unusually inflated giant planet is the star it orbits. We know from both theory and observation that giant planets, hot Jupiters, tend to be larger than planetary formation models predict based on their masses alone. The standard explanation for this is stellar irradiation. The planet sits so close to its star that it receives an enormous flux of radiation, and this energy is deposited into the planet's outer layers, heating them and causing the atmosphere to expand outward. The planet puffs up like a loaf of bread in an oven. The more intense the stellar heating, the more inflation you expect. This is the ohmic dissipation mechanism, or more broadly the family of irradiation-driven inflation models. They have had real success in explaining why many hot Jupiters are larger than models built for isolated, free-floating giant planets would predict. The general trend is clear. Hot Jupiters close to their stars are larger than ones that sit farther away. Irradiation inflates them. For WASP-193b, this mechanism is certainly operating. The planet sits extremely close to a luminous F-type star. It is, by any measure, intensely irradiated. The equilibrium temperature of the planet, the temperature it reaches when it absorbs starlight and re-radiates that energy as infrared, is estimated to be over 1000 Kelvin. It is a furnace. But here is the problem. While irradiation inflation works well for explaining why hot Jupiters are somewhat larger than isolated models predict, it struggles when the inflation is extreme. The typical inflated hot Jupiter might be 10 or 20% larger than models suggest. Some of the more extreme cases might be 50% larger. WASP-193b is not just mildly or even dramatically inflated. It is inflated to a degree that stellar irradiation alone, in the form of any mechanism currently understood, cannot plausibly account for. The physics of stellar irradiation and its interaction with a planet's interior is complex. Energy deposited in a planet's outer atmosphere does not automatically translate into the planet getting physically larger. The relationship between deposited energy and radius inflation depends on where in the interior the energy is being deposited, how the planet's internal convection responds, and what the planet's structure looks like at depth. For irradiation to produce the kind of inflation we see in WASP-193b, the efficiency of energy transport into the deep interior would need to be extraordinarily high, higher than we have strong reasons to believe is possible, given what we understand about planetary interiors. There are several specific mechanisms that have been proposed over the years for how stellar irradiation might drive inflation. An ohmic dissipation posits that the stellar irradiation drives atmospheric circulation at high altitudes, and that this circulation interacts with the planet's magnetic field to generate electric currents that then dissipate as heat in the planet's deep interior. The idea is clever and has some theoretical support, but scaling it up to explain an object as inflated as WASP-193b requires pushing the mechanism into regimes where it may not be efficient enough. Another mechanism invokes tidal heating. When a planet orbits its star in an elliptical rather than perfectly circular orbit, the tidal forces from the star flex and deform the planet slightly as it moves closer to and farther from the star during its orbit. This tidal flexing generates heat inside the planet, just as squeezing a rubber ball generates warmth in your hands. Tidal heating is responsible for the extraordinary volcanism on Io, Jupiter's moon, which sits in a gravitational tug-of-war between Jupiter and the other large moons. Could tidal heating of WASP-193b account for its extreme inflation? The challenge here is that planetary orbits tend to circularize over time precisely because of tidal dissipation. Yeah, a planet that has been orbiting its star for long enough, and WASP-193b's star is not a young star, should have had enough time to settle into a nearly circular orbit, at which point tidal heating becomes negligible. Unless something is maintaining orbital eccentricity, another currently unseen planet in the system perturbing the orbit, tidal heating does not obviously sustain the kind of inflation we observe. None of these mechanisms are ruled out. None of them are clearly sufficient. The honest scientific position is that irradiation-driven inflation of some kind is likely contributing to WASP-193b's unusual size. It would be strange if it weren't, given how much radiation the planet receives. But that irradiation alone, through any mechanism currently understood, does not seem adequate to fully explain the measured density. To truly grapple with WASP-193b, we need to think about what this planet might actually look like. Not from a distance, not as a point of light being measured from afar, but in physical terms, as a three-dimensional object existing in space. Start from the outside. If you were somehow able to approach WASP-193b, ignore for the moment the crushing radiation from the nearby star, the complete lack of anything resembling a spacecraft capable of this journey. What would you see as you approached? You would see an enormous sphere, larger than Jupiter, softly lit by the pale, intense light of its F-type parent star. From a distance, it might look not entirely unlike a gas giant in our own solar system. It would probably have cloud bands, are driven by atmospheric circulation patterns influenced by its intense irradiation on one side, because a planet this close to its star is almost certainly tidally locked, always showing the same face to its sun. The day side would be blisteringly hot, perpetually illuminated. The night side would be cold and dark, at least relative to the face pointing toward the star. But as you got closer, you would begin to notice something different. Something is wrong about the scale of it. The atmosphere is not ending where you expect it to end. As you descended, if we can call it that since you would essentially be falling into increasingly dense gas, the atmosphere would go on and on and on. The transition from essentially nothing to something you could meaningfully call atmosphere would be extraordinarily gradual. Because with almost no gravity to compress things, with such a tiny fraction of Jupiter's mass despite this enormous volume, the atmosphere would extend upward to staggering altitudes. This is one of the key physical consequences of WASP-193b's low density. Its gravity is extraordinarily weak for something this big. In planetary physics, there is a quantity called surface gravity, the gravitational acceleration at the top of the gaseous atmosphere, or at the solid surface if one exists. On Earth, surface gravity is about 9.8 meters per second squared, what we call 1g. On Jupiter, despite being a gas giant, surface gravity is about 24.8 meters per second squared, about 2.5 times Earth's. The sheer mass of Jupiter, concentrated in a sphere even as large as it is, creates a strong gravitational pull. For WASP-193b, the surface gravity is estimated to be well below Jupiter's and likely below Earth's, despite the planet's enormous size. A planet this massive, in solar system terms, the 44. Earth masses is not nothing, but spread out over 3 times. Jupiter's volume experiences a dramatic dilution of gravitational force at its surface. Low gravity means gas can extend further outward, before becoming too tenuous to maintain a coherent atmospheric structure. This is part of why WASP-193b is as large as it is. The gas just does not have anything compelling it to pack tightly together. Imagine filling a room with fog. Now imagine that the room is slightly smaller, but the fog is compressed by a fan pushing it inward. The compressed fog is denser. The uncompressed fog, allowed to fill whatever space is available, spreads further. WASP-193b's atmosphere is the uncompressed fog. The gravity barely cares enough to squeeze it down. This creates an atmosphere that is, in a literal sense, almost ocean-like in its depth. Not an ocean of liquid, but an ocean of gas, extending through thousands and thousands of kilometers before the density finally climbs to the point where you would encounter anything resembling the deep interior, if a deep interior exists in any meaningful sense. For a planet this light, there's distinction between atmosphere and interior blurs. There may not be a meaningful phase transition, a clear boundary where the gas gives way to something denser and more solid. It might just be gas gradually becoming more compressed gas, all the way down. This is a profoundly alien kind of world. It is not a gas giant in the familiar sense, not a mini Jupiter with a solid or liquid core and a thick atmospheric envelope wrapped around it. It might be more accurately thought of as a diffuse gas sphere held together by gravity that is only barely adequate for the job. One of the more fascinating and recently developed ideas for explaining super-puff planets like WASP-193b is the concept of reinflation. Here is how it works. When a giant planet first forms while it is still young, it is hot from the energy of accretion, the process of gathering up material. A newly formed gas giant glows from within. Its interior is still radiating the heat produced during formation. This early thermal energy naturally inflates the planet. Hot gas takes up more volume than cold gas, so young giant planets are generally larger than old giant planets. Over time, the planet cools. As it radiates this internal heat away into space, the gas contracts and the planet shrinks. After billions of years, an isolated gas giant sitting far from its star would be significantly smaller than it was when it first formed. This is the normal evolutionary trajectory. Cool down, compress, settle. For hot Jupiters, though, the story can diverge from this. Because they are so close to their stars, they receive a constant influx of stellar radiation that supplements whatever internal heat remains. This radiation can slow the cooling process, keeping the interior warmer than it would otherwise be, and maintaining the planet's inflated size to some degree. But reinflation goes one step further than simple sustained irradiation. Reinflation is the idea that a planet can actually grow larger again after having previously contracted if its host star becomes more luminous over time. Stars are not static, they evolve. A main sequence star like WASP-193 changes its luminosity over the course of its lifetime. Generally, stars on the main sequence grow slightly more luminous as they age, as the hydrogen-burning core gradually adjusts. More dramatically, when a star begins to leave the main sequence and evolve toward becoming a subgiant or a red giant, its luminosity increases substantially. For a planet that has previously cooled and contracted somewhat, this renewed surge of radiation from a brightening star could, in principle, pump enough energy back into the planet's outer layers to cause a second inflation event, like if WASP-193b experienced a period of reinflation. If its star has been slowly brightening over time and has delivered increasing amounts of radiation to the planet over the last billion years, this could account for some of the extreme puffiness we observe today. The planet might have been more compact in the distant past, then swelled outward as its star brightened. It would currently be in the middle of an ongoing inflation process, still responding to increasing irradiation. This is not merely speculation. There are theoretical models that predict reinflation under realistic stellar evolution scenarios, and WASP-193b's orbit, extremely close, receiving intense radiation from an F-type star, puts it squarely in the regime where reinflation models predict significant effects. And if the current inflation is partly the result of reinflation driven by stellar evolution, then WASP-193b is not in a stable equilibrium state. It is a planet in transition. It is actively becoming something different from what it was in the past. This idea carries a haunting implication. If WASP-193b is being inflated by its star's increasing luminosity, then over time the inflation may continue or even intensify. The planet may become even larger and even less dense as its star continues to evolve. At some point, the outer layers of the atmosphere may reach escape velocity, or rather, the energy deposited in the upper atmosphere by stellar radiation may exceed the gravitational binding energy holding those layers to the planet. And then the atmosphere will begin to leak away, which brings us to perhaps the most urgent question in the entire WASP-193b story: mass loss, atmospheric escape, photo-evaporation. These are the terms astronomers use to describe a process that, once you understand it, sounds almost catastrophic, except that it operates on timescales so long that catastrophe is perhaps not the right word. It is more like a slow exhalation, a planetary exhale that lasts hundreds of millions or billions of years. Here is the basic mechanism. The upper atmosphere of any planet, even Earth, is constantly bombarded by ultraviolet and X-ray radiation from the parent star, collectively referred to as high-energy radiation. When these high-energy photons hit gas molecules in the upper atmosphere, they can transfer enough energy to break the molecule apart and give the fragments enough kinetic energy to exceed the planet's escape velocity. These particles then fly off into space, bombing never to return. Over enormous timescales, this process can strip away significant amounts of a planet's atmosphere. For most planets, this process operates slowly and has a limited total effect. Earth loses some of its atmosphere this way. Some hydrogen atoms from the top of the thermosphere trickle away into space, but at rates that have no meaningful impact on geological or evolutionary timescales. The gravity of a rocky planet like Earth is strong enough to retain its atmosphere against all but the most extreme irradiation environments. For gas giants, the situation is more complex. The hydrogen and helium in a gas giant's outer atmosphere are light atoms and molecules, easier to strip than the heavier molecules in rocky planet atmospheres. But gas giants are also very massive, near with correspondingly strong gravity that makes it harder for gas to escape. The balance between irradiation rate and gravitational binding energy determines whether atmospheric escape is significant or negligible. For WASP-193b, this balance is deeply precarious. Consider, the planet sits extremely close to a hot, luminous star. It receives an enormous flux of ultraviolet and X-ray radiation. At the same time, its gravity is feeble, far weaker than you would expect for a planet this large, because there is so little mass distributed across such a large volume. The gravitational binding energy of the outer atmosphere, the energy needed to lift the outermost gas off the planet and send it into space, is surprisingly low precisely because the planet's surface gravity is low. This combination, intense irradiation from a nearby star and weak gravity unable to firmly hold the atmosphere, puts WASP-193b in a potentially precarious position. There are several mechanisms by which it might be losing mass right now, as you read these words. The most commonly discussed is photoevaporation. High-energy photons from the star eat the upper atmosphere to the point where gas moves fast enough to escape. In the most extreme version of this process, called hydrodynamic escape, the heated atmosphere behaves somewhat like a wind blowing outward from the planet, dragging gas continuously into space in a structured flow, rather than just individual fast-moving particles. The paper announcing WASP-193b's discovery, and the subsequent scientific discussion around it, noted that this planet appears to be a candidate for significant ongoing mass loss. The current structure of the planet, the extreme inflation, the low density, the proximity to a luminous star, the weak gravitational field, all point toward a world that is probably not in a stable equilibrium, but in a state of ongoing transformation. If WASP-193b is losing mass, the process could be operating at a remarkable rate. Some models of photoevaporation for extreme cases, and WASP-193b is as extreme as it gets, suggest mass loss rates that could, over billions of years, strip away a substantial fraction of the planet's current atmosphere. The planet might evolve from a bloated superpuff into something considerably smaller as the outer layers are steadily lost to space and the denser, deeper layers contract under the planet's own gravity. There is something almost melancholy about this image, a planet that formed enormous and diffuse, bathed in radiation that is slowly, inexorably consuming it, reducing it year by year and millennium by millennium to something more compact and ultimately smaller than what it was, like watching an ice sculpture melt in summer sunlight, except the ice sculpture is the size of Jupiter and summer lasts 1 billion years. But here is an important caveat. We do not yet have direct observational evidence of ongoing mass loss from WASP-193b. This is the theoretical prediction based on the planet's properties, not a confirmed observation. Detecting atmospheric escape from a planet 1,200 light-years away is technically very challenging, but it requires looking for specific signatures in the planet's transmission spectrum, the light that filters through its atmosphere when it transits, and searching for markers of escaping hydrogen or helium. These are observations that future telescopes, and in particular the James Webb Space Telescope, are potentially capable of making. But as of now, we know the conditions are right for mass loss to be occurring. We do not yet know at what rate it is actually happening, or how long WASP-193b has already been losing mass, or what its evolutionary future looks like in detail. What we do know is that the planet is, at this moment, in conditions where its long-term fate is uncertain. It is a world in motion, not in the sense of its orbital dynamics, but in the deeper sense of its physical evolution. And that makes it not just a static curiosity, but a dynamic puzzle. If the present state of WASP-193b is mysterious, its past is perhaps even more so. How does something like this form? Planet formation is a field that astronomers have been building, refining, and arguing about for decades. The broad strokes are reasonably well established. Planets form in protoplanetary disks, flattened clouds of gas and dust that surround young stars in their early years. Within these disks, dust particles collide and stick together, building up into pebbles, then rocks, then planetesimals, then embryonic planets. Eventually, the biggest embryos sweep up most of the nearby material and become the dominant planets in the system. For giant planets, there are two main competing formation pathways, and understanding which one is relevant to a particular planet matters enormously for understanding what that planet is made of and how it ended up where it is. The first pathway is core accretion. This is the dominant model for the formation of Jupiter and Saturn in our solar system. It goes like this. A solid core, rock and E, assembles first, reaching roughly 10 to 15 Earth masses over timescales of a few million to perhaps tens of millions of years. Once the core is massive enough, it begins drawing in gas from the surrounding disk in a runaway process. The gas envelope grows rapidly, eventually dwarfing the core. The result is a gas giant with a solid, or possibly liquid metallic core buried beneath a vast envelope of hydrogen and helium. The core accretion model works well for Jupiter. It works less well for certain super-puff planets, because it predicts a core that should contribute meaningfully to the average density. And for a planet as diffuse as WASP-193b, even a modest 10 Earth mass rocky core, dense at perhaps 5 grams per cubic centimetre, would pull the average density upward significantly. For the overall density to sit at 0.059, either the core is very small, perhaps only a few Earth masses at most, or it is extremely diffuse itself, which seems contradictory for a rocky body. The second pathway is disk instability. In this scenario, the protoplanetary disk itself becomes gravitationally unstable in regions where the gas density is high enough and the temperature is low enough. Thus, clumps of gas can collapse directly under gravity without going through the slow pebble-building phase. The resulting planet forms quickly, in perhaps a few thousand years rather than millions, and it is primarily gaseous from the start with little or no solid core. Disk instability produces planets that are fundamentally different in character from core accretion planets. They are born as gas balls. They might accumulate some solid material over time, but the initial object is gas-dominated. This is potentially consistent with a very low average density, because there is no dense rocky core anchoring the density upward. However, disk instability has its own challenges as an explanation for WASP-193b. Disk instability is thought to be most efficient at large distances from the star, the outer regions of protoplanetary disks, and where conditions are right for instability to develop. But WASP-193b orbits extraordinarily close to its star. Did it form far out and migrate inward, or did it somehow form close in through a mechanism that is not well understood? Planet migration is real and necessary for explaining the existence of hot Jupiters in general. The current consensus is that most hot Jupiters did not form where they are. They formed at larger orbital distances beyond the snow line where volatile ices could contribute to their mass, and then migrated inward through interactions with the protoplanetary disk or through gravitational interactions with other bodies in the system. This migration can be dramatic, carrying a planet from the outer reaches of a planetary system all the way to an orbit with a period of just a few days. Could WASP-193b have formed in the outer disk through disk instability, producing a very gas-rich, low-density world with minimal solid core, and then migrated inward to its current scorchingly close orbit? This narrative is not impossible, but it requires the planet to have survived the migration without losing too much of its mass, and without its close-in orbit dramatically destabilizing its structure before we observe it. Given how extreme the planet's current properties are, threading this needle of formation and migration history feels like asking a lot from models that were not designed with WASP-193b specifically in mind. A third possibility, less developed but worth mentioning, is that WASP-193b is not a typical gas giant at all in its composition. Some researchers have proposed that superpuff planets might harbour extended, optically thick rings of dust or debris that make the transit appear larger than the planet itself actually is, effectively inflating the apparent radius, while the true planetary body is smaller and denser. Under this hypothesis, what we measure as the radius of the planet in transit is partly the radius of a disk of particulate material surrounding the planet. This would mean the true density is higher than it appears. This is an interesting idea, and it has been applied to some superpuff candidates with some success in reducing the apparent strangeness of their densities. But for WASP-193b, the extreme nature of the density, 0.059 grams per cubic centimetre, is severe enough that rings alone seem unlikely to fully account for it. The constraints from the transit light curve and the detailed modelling of how rings would appear in observations make this a challenging explanation to sustain for WASP-193b at its measured properties. It cannot be dismissed outright, but it is not the leading explanation. The honest answer to the formation question is that we do not yet know how WASP-193b came to be the way it is. The standard formation pathways produce something somewhat like it under certain conditions, but none of them naturally and comfortably produce something exactly like it. WASP-193b may have formed through a combination of unusual circumstances: a particular disk composition, a specific migration history, an unusually gas-rich formation environment that does not map cleanly onto any of our existing theoretical frameworks. And perhaps that is the most scientifically valuable thing about it. In science, the objects that do not fit neatly into existing categories are often the most informative. They force you to ask whether your framework is missing something. They push you to build new theories, refine old ones, and look more carefully at your assumptions. All of the science we've discussed so far, the density, the mass, the radius, the possible explanations, has been derived largely from photometry and radial velocity measurements. We have measured the size of the planet and more laboriously its mass. From those we have calculated its density and tried to reason backward about what it might be made of. But in a sense, we have been reading the planet from the outside, deducing its nature from indirect signatures without ever directly analysing its composition. That is about to change, and it is here that the James Webb Space Telescope enters the story. JWST, launched on Christmas Day 2021 and achieving its first science operations in 2022, is the most powerful space telescope ever built for astronomical observations in the infrared. It is an observatory of unprecedented sensitivity, designed in part specifically to answer the kinds of questions that WASP-193b poses. One of its primary science goals is the characterization of exoplanet atmospheres, and its main tool for this is transmission spectroscopy. Transmission spectroscopy works during a transit. When a planet passes in front of its star, it does not just block starlight with a uniform opaque disk. The outer atmosphere of the planet, the thin shell of gas at the very edge, is not fully opaque. Light from the star filters through this outer atmosphere, and as it does, different wavelengths of light are absorbed to different degrees by the molecules present. Hydrogen absorbs at certain wavelengths, water vapor absorbs at others, methane, carbon dioxide, sodium, potassium, helium. Each has a distinctive spectral fingerprint that reveals its presence when you compare the spectrum of the star during transit with the spectrum of the star outside transit. This technique has been used with previous telescopes to detect molecules in exoplanet atmospheres, but JWST's sensitivity and wavelength range make it transformatively more powerful than anything available before. Where Hubble could detect broad features indicating the presence of certain molecular classes, JWST can potentially measure detailed molecular abundances, thermal profiles, and atmospheric dynamics in exoplanet atmospheres that are hundreds of light years away. For WASP-193b, transmission spectroscopy offers the possibility of finally putting real constraints on what the atmosphere is made of. If the atmosphere is dominated by hydrogen and helium, the lightest gases, this would be consistent with a planet that formed in a gas-rich environment and has remained gas-dominated. If heavier molecules like water vapor or methane are detected in abundances that can be measured, this would constrain the planet's bulk composition and formation history. The ratio of carbon to oxygen in the atmosphere, for instance, is thought to preserve information about where in the protoplanetary disk the planet formed, because different volatile compounds freeze out at different temperatures and distances from the star. There's another reason. WASP-193b is an exceptionally valuable target for JWST. Its inflated, extended atmosphere means that the transmission spectrum signal is amplified. When a planet's atmosphere is puffed out to large altitudes, as WASP-193b's almost certainly is given its low gravity, there is more atmosphere for starlight to pass through during transit. The spectral signatures are correspondingly stronger, while making them easier to detect with a given telescope sensitivity. A denser, more compact atmosphere around a smaller planet would produce weaker signatures that require more observing time to detect. WASP-193b's extreme inflation is, in a sense, an accidental advantage for atmospheric science. The planet that is so puzzling to form theorists is also an ideal target for atmospheric observers. Its strangeness makes it hard to understand and simultaneously easier to study. If JWST observations were to detect, for example, unusually high abundances of helium in the upper atmosphere, perhaps escaping the planet in a structured outflow, this would be direct evidence of ongoing atmospheric mass loss. Helium escaping from close-in giant planets has been detected around other exoplanets, and its detection around WASP-193b would immediately tell us something profound about the planet's current state and its evolutionary trajectory. Conversely, if the atmosphere appears unexpectedly rich in heavy molecules, this would challenge the assumption that the planet is primarily a hydrogen-helium world. It might point toward exotic atmospheric chemistry driven by the intense irradiation, or toward a formation history that enriched the atmosphere in metals far beyond what we see in Jupiter or Saturn. And if the atmosphere turns out to be simpler and cleaner than expected, if it is largely featureless in transmission, dominated by clouds or hazes that suppress spectral features, that too would be informative, though more challenging to interpret. It would mean we need to look deeper or in different wavelength windows to understand what lies beneath. Any of these outcomes would advance our understanding of this remarkable planet, and what is genuinely exciting is that we may not have to wait much longer. WASP-193b is bright enough, close enough in apparent brightness terms, and unique enough scientifically that it is a high-priority target for detailed study. The era of truly understanding this planet, rather than merely marvelling at its strangeness, may already be beginning. There is something philosophical lurking inside the physics of WASP-193b that deserves more attention than it usually receives. We tend to think of gravity as a universal, constant presence, the force that holds things together, that shapes orbits and keeps atmospheres in place, and makes everything in the universe structured rather than randomly scattered. And in a broad sense it is. Gravity is everywhere. It is inescapable. But gravity is not the same everywhere. The strength of gravity at the surface of a world depends on two things: the mass of that world and the distance between you and its centre. For a planet with Jupiter's mass compressed into Jupiter's volume, you get a surface gravity of 24.8 meters per second squared. For the same mass spread out into twice the volume, the surface gravity would drop, because you're now farther from the centre of mass. And for a much smaller mass spread out into a comparable or larger volume, the surface gravity drops dramatically. WASP-193b has a surface gravity that is, depending on exactly where in the atmosphere you define the surface, comparable to or possibly somewhat below that of Earth. Not as low as the surface gravity of a small moon, but far lower than Jupiter, and low enough that the experience of existing inside this planet's gravitational field would be entirely unlike what you know from any solar system world. Consider what low surface gravity means for atmospheric physics. On Earth, the atmosphere decreases in density with altitude in a pattern determined by a quantity called the scale height, the altitude over which atmospheric pressure drops by a factor of about 2.7. Earth's scale height in the lower atmosphere is about 8 kilometers. Jupiter's, despite being a gas giant, has a relatively modest scale height because of its strong gravity. For WASP-193b, with its low gravity and very high temperature, hot atmospheres have higher scale heights because the gas is moving faster. The scale height is predicted to be enormous, perhaps hundreds of kilometers. This means the atmosphere thins out extremely gradually with altitude extending to enormous heights before becoming effectively negligible. This extended atmospheric profile is not merely a quirk. It has real physical consequences. It means that the planet's gravitational grip on its outermost atmospheric layers is genuinely weak. Gas molecules in the uppermost layers of WASP-193b's atmosphere experience gravitational acceleration that is already reduced by their distance from the planet's center, and the energy required to lift them off the planet entirely is correspondingly small. Under the influence of intense stellar radiation heating these upper layers, escape becomes plausible where it might be negligible for a more compact world. There is also something deeply interesting about what low gravity means for the planet's internal dynamics. In Jupiter, the enormous mass creates such powerful internal pressure that hydrogen deep in the interior transitions into a metallic and electrically conducting fluid, metallic hydrogen, a state that does not exist naturally anywhere on Earth and that generates Jupiter's powerful magnetic field. In Saturn, a similar but less extreme version of this occurs. For WASP-193b, with only about 44 Earth masses distributed over a volume 3 times Jupiter's, the internal pressure is vastly lower. Whether metallic hydrogen forms in the deep interior is uncertain, but the conditions for the extreme phase transitions that occur in Jupiter and Saturn are probably not present in the same way. The planet's interior may be qualitatively as well as quantitatively different from the gas giants we know best. A giant planet without metallic hydrogen in its interior would have a fundamentally different magnetic field structure, weaker, perhaps, or organized differently. If this has implications for how the atmosphere responds to the stellar magnetic environment, how energetic particles from the parent star interact with the planet, and how the outer atmosphere is driven by stellar wind. These are all open questions because we cannot directly measure WASP-193b's magnetic field from here. But they are questions that future generations of instruments may be able to address. The gravity of WASP-193b is not just a number. It is a key that unlocks a cascade of consequences for the planet's structure, its atmosphere, its interior, its magnetic environment, and its long-term fate. And that number, substantially lower than Jupiter's, implies a world that is not just physically unusual but dynamically unusual in ways we are still working through. Let us be precise about where planetary science stands with respect to WASP-193b, because vague hand-waving about our models are challenged is not satisfying when we can actually be specific about what the models predict and where they fail. Well, the standard framework for understanding the sizes of hot Jupiters, the models we use to predict how large a planet of a given mass at a given orbital distance around a given star should be, is a well-developed area of planetary science. These models are built on fundamental physics, hydrostatic equilibrium, the balance between the outward pressure of gas and the inward pull of gravity, equations of state describing how matter behaves at different temperatures and pressures, radiative transfer equations governing how heat flows through the planet, and in recent years prescriptions for how stellar irradiation deposits energy in the outer layers. When you run these models for a planet with WASP-193b's mass, at WASP-193b's orbital distance, around a star with WASP-193b's luminosity, you get a predicted radius. That predicted radius is substantially smaller than the measured radius, not slightly smaller, substantially smaller. The gap between what the models predict and what is observed is sometimes quantified in terms of what fraction of the planet's total energy budget needs to be deposited into the deep interior as opposed to the outer atmosphere. to reproduce the observed inflation. For typical inflated hot Jupiters, explaining the inflation requires that something like 1% of the total stellar irradiation reaching the planet be converted into internal heating and deposited deep in the interior. This is already a modest but not implausible efficiency for some of the mechanisms we discussed. For WASP-193b, the discrepancy is so large that the required internal heating efficiency becomes problematic. The planet is so much larger than models without significant internal heating. Predict that matching the observation requires either an extraordinarily high heating efficiency or a combination of mechanisms working together, or something else entirely that is not currently in the models. The standard toolkit is being stretched. There is also a structural constraint worth mentioning. For any given mass, there is a theoretical maximum radius for a gas giant, a size beyond which adding more hydrogen and helium does not make the planet larger, because the self-gravity of the material starts compressing it. Planets near this maximum theoretical radius have the minimum possible density for their mass. WASP-193b appears to be approaching or possibly at this theoretical maximum for its mass, which means that if the standard equations of state are correct, the only way to explain its size is to invoke some mechanism that is either dumping vast amounts of energy into the planet's interior or somehow altering the equation of state. Some theorists have explored whether unusual atmospheric chemistry, particular types of absorbers in the upper atmosphere that trap heat more efficiently than standard hydrogen-helium models assume, might contribute to the inflation. Others have looked at whether circulation patterns on the tidally locked day-night interface of the planet might somehow pump energy from the irradiated day side to the deep interior more efficiently than simple models predict. None of these ideas are wrong exactly, and many of them may be operating at some level. The problem is that each of them individually seems insufficient to bridge the full gap between the standard model prediction and the observed radius of WASP-193b. And when you try to combine multiple mechanisms together to say, perhaps it is a combination of all these things, you run into the risk of overfitting. Constructing a just-so story that explains this one planet but does not give you predictive power for understanding others, the most intellectually honest position is that WASP-193b presents a genuine challenge to current models. The challenge is not at the level of our models are slightly off and need minor tweaks. It is at the level of our models are missing something significant, and this planet is showing us where the gap is. And that kind of challenge is, in the long history of science, the kind that tends to generate real progress once we figure out what we are missing. There is a precedent worth examining here. Before we had WASP-193b, before we had the current generation of superpuff planets as a named category of objects, there were the hot Jupiters, and specifically the inflated hot Jupiters that the early years of transit surveys kept turning up. When the first inflated hot Jupiters were discovered in the early 2000s, planets with densities noticeably lower than the standard models predicted, there was genuine scientific controversy. Were the density measurements right? Were the stellar radius estimates correct? Was there something wrong with the models? Or were there real physical mechanisms operating at levels not previously accounted for, producing these inflated worlds? The answer, which took years to work out and required both better observations and better theory, was all of the above in different proportions for different planets. Some inflation claims were inflated themselves. Titan measurements showed the planets were less extreme than initially thought. but a significant fraction of the inflated hot Jupiters were real, although their densities were genuinely lower than standard models predicted, and this required the development of new theoretical mechanisms, particularly the various irradiation-driven inflation models, to explain. The process was messy and slow. It involved debates about whether ohmic dissipation was efficient enough, whether tidal heating was relevant, whether there were corrections to the equations of state at the relevant pressure-temperature conditions. None of the mechanisms were immediately obvious or immediately accepted. The community had to investigate, propose, test, refine, and gradually converge on a set of ideas that, while still not complete, gave a workable account of inflation for most hot Jupiters. WASP-193b sits beyond the edge of that converged understanding. It is too extreme even for the explanations that work for the moderately inflated hot Jupiters. It is like a piece of evidence that says, you have figured out most of the story, but not all of it. There is another chapter. What the hot Jupiter inflation story teaches us is that discovering an unexplained phenomenon is not a failure of science. It is science working correctly. The unexplained phenomena push the field forward. They force new theories. They motivate new observations. They eventually yield understanding that would never have been reached by examining only the comfortable, well-explained cases. And there is something deeply encouraging about that history when you look at WASP-193b. The planet that seems to break our understanding today is probably the planet that will, in 10 or 20 years, be a solved case, or at least a much better understood one. The astronomy community is not puzzled by WASP-193b and giving up. It is puzzled by WASP-193b and leaning in, excited by the prospect of finding what is missing. WASP-193b exists within a context that is worth pausing to appreciate: the extraordinary diversity of the exoplanet population as a whole. When the first exoplanet around a Sun-like star was confirmed in 1995, 51 Pegasi b, a hot Jupiter orbiting almost impossibly close to its host star, it immediately overthrew the idea that our solar system was a typical template for what planetary systems look like. 51 Pegasi b was nothing like any planet in our solar system. It was a gas giant at 1/20th the distance of Mercury from its star, completing an orbit in about 4 days. It was absurd by the standards of solar system science, and yet there it was. In the nearly 3 decades since then, exoplanet astronomy has revealed a universe that is more varied, more creative, more strange than almost anyone initially imagined. Yeah, we have found planets orbiting 2 suns simultaneously, moving in figure-8 gravitational dances around binary star systems. We have found planets that almost certainly have iron rain in their atmospheres, tidally locked worlds where the dayside temperature exceeds 2000 Kelvin, hot enough to vaporize certain metals, which then condense and rain down on the cooler night side. We have found planets smaller than Earth and denser than iron. We have found water worlds, possibly covered entirely in global oceans, with hydrogen envelopes making them look like undersea planets wrapped in gas. We have found planets in the habitable zones of red dwarf stars that experience such intense stellar flares they may be continuously sterilized. Super-puff planets like WASP-193b fit into this picture as one more reminder that the universe has been running planetary formation experiments for billions of years across trillions of star systems, and that the results of those experiments include outcomes we had not predicted and are still struggling to explain. Among the exoplanet population, superpuffs are relatively rare. Most planets, even most gas giants, even most hot Jupiters, have densities that fall within the range of what our models can explain, at least approximately. The extreme outliers like WASP-193b are a small fraction of confirmed planets, but their rarity does not make them less important. If anything, it makes them more valuable scientifically, because rare objects with extreme properties are often the best probes of the boundary conditions of theoretical models. They are the stress tests. An analogy. If you want to understand the structural limits of a material, you don't just apply modest forces and observe modest deformations. You push it to its limit. You find out where it breaks. The breaking point tells you something about the material's fundamental properties that gentle testing cannot. WASP-193b is, in this sense, a stress test for planetary physics. It is pushing models to their breaking points, and what breaks and what holds will tell us something fundamental. The diversity of exoplanets has also changed the way we think about the meaning of our own solar system. For a while after 51 Pegasi b, there was a worry that our solar system, with its outer gas giants and inner rocky planets, its orderly progression from small to large and back, might be unusual. If hot Jupiters are so common, maybe solar systems without them are the oddities. The Kepler mission put this concern in perspective. It showed that the most common kind of planet in the galaxy is neither a Jupiter-type gas giant nor an Earth-type rocky world, but something in between, the so-called super-Earths and mini-Neptunes, planets ranging from about 1.5 to 3.5 times Earth's radius, which do not exist in our solar system at all. Our solar system, which lacks this most common type of planet, may itself be somewhat unusual, not unique. Probably there are millions of solar systems with outer gas giants and inner rocky planets, but not the universal template either. WASP-193b is not a super-Earth or a mini-Neptune. It is at the opposite extreme, an inflated giant, not a compact small world. But it speaks to the same broader lesson. Planetary systems come in extraordinary variety, shaped by physics that plays out in different ways in different environments, producing an almost bewildering range of worlds. We have touched on this before, but it deserves its own focused discussion. Measuring the mass of WASP-193b was genuinely, technically difficult. Radial velocity measurements are hard in general. You're looking for tiny shifts in spectral lines produced by stellar wobbles of meters per second, embedded in spectra from stars that are many light years away. The precision required is extraordinary, and the noise sources are many. Stellar activity, sunspots, magnetic variations, surface oscillations can produce spectral shifts that mimic planetary signals, instrumental systematics, atmospheric effects from Earth's own atmosphere, calibration uncertainties. All of these must be carefully managed. For WASP-193b, the challenge is particularly acute because the planet, despite its enormous size, has such a small mass. A small mass means a small stellar wobble. A small stellar wobble means a small radial velocity signal. A small radial velocity signal is hard to distinguish from noise. The signal-to-noise requirements for reliably detecting and characterizing WASP-193b's mass are correspondingly high. The Discovery team reported that WASP-193b was detected with radial velocity measurements using multiple spectrographs, including instruments with excellent precision and stability. But the mass measurement still carries meaningful uncertainties. This is not a criticism of the observers. This is the state of the art for a planet with these properties. The best we can do with current instruments gives us a mass with error bars that, while sufficient to confirm the planet's low-density nature, leave room for refinement. Why does this matter? Because the density we calculate, and all the physical interpretation that flows from it, depends on the mass. If the mass turns out to be somewhat higher than the current central estimate, the density goes up, and the planet is somewhat less extreme. If the mass is lower, the density goes down and the planet is even more extreme. The current measurements place the planet firmly in the realm of extreme superpuffs, but future, more precise radial velocity observations could sharpen our understanding of exactly how extreme it is. There is also the question of whether the radial velocity signal from the planet could be contaminated by stellar activity in ways that are hard to disentangle. F-type stars like WASP-193 can be somewhat active, with magnetic cycles and surface convection patterns that introduce noise into radial velocity measurements. Sophisticated statistical techniques exist to separate planetary signals from stellar activity signals, and the Discovery team applied them, but the challenge is real. Future spectrographs, instruments designed specifically for extreme radial velocity precision, like the ELTHIRES instrument, planned for the extremely large telescope, could potentially measure the mass of WASP-193b with substantially better precision. Better mass measurements would not change the fundamental strangeness of the planet, but would constrain it more precisely and give theorists better numbers to work with when testing formation and evolution models. This is a theme that runs through all of exoplanet science. The measurements we have are good enough to tell us something genuinely surprising and important, but they're not yet good enough to answer all the questions that the surprising results raise. Progress in exoplanet science is therefore always a two-pronged effort. Better theories and better measurements advancing together, each informing the other. The nickname Cotton Candy Planet for WASP-193b deserves a moment of reflection. It is, of course, a simplification. Cotton candy and a planet are not the same thing. The comparison is purely about density, extracted from the rich complexity of what a planet is, and reduced to a single number that happens to match a familiar material. The analogy is not meant to be taken literally. Nobody is suggesting that WASP-193b is spun sugar, or that if you could reach it and eat it, it would be sweet. The physics of what this planet is are far stranger and more complex than any kitchen analogy can capture, and yet the nickname captures something real. It communicates, quickly and viscerally, just how improbably light this planet is. It gives a human anchor to a number, 0.059 grams per cubic centimetre, that is otherwise abstract. Most people have held a clump of cotton candy in their hands, felt how it seemed to be almost nothing, how it dissolved at the slightest pressure. If you're told that a planet has the same density as that, something in your intuition recoils because a planet is supposed to be heavy. That recoil is appropriate. It reflects the genuine strangeness of the discovery. Science has a long tradition of memorable nicknames for extraordinary objects. Hot Jupiters were hot Jupiters before anyone had figured out why they were where they were. The name captured the central paradox. Neutron stars were neutron stars from almost the beginning of their theoretical conception. Pulsars, quasars, magnettaires. The names all reach for something memorable that encodes the essential weirdness. Superpuffs as a category, and cotton candy planets as a subset of superpuffs, are part of this tradition. The informality is intentional. Formal scientific names for categories extremely inflated low-density transiting gas giants are precise but forgettable. Cotton Candy Planet is neither precise nor forgettable, and in the context of science communication, the latter quality has real value. It makes people pay attention. It makes them ask questions. It brings them to a conversation about density and planetary formation that they might otherwise never have had. There is something almost fitting about a planet this strange having a name this strange. WASP-193b lives at the edge of what we understand, at the boundary between the expected and the impossible. A planet with a perfectly ordinary name would, in some small way, undersell the situation. Let us do a final tour of comparison, not to diminish the strangeness of WASP-193b, but to frame it within the full context of what we know about planetary densities and what they imply. Saturn, 0.69 grams per cubic centimetre, the lightest planet in our solar system. Saturn is light enough to float on water. Saturn's low density is the result of a combination of factors. It is a hydrogen-helium world, less massive than Jupiter and therefore less self-compressed. With an internal structure that is still the subject of active research regarding the nature of its core and the extent of its fuzzy density transition zone. But Saturn's density is 11 times higher than WASP-193b's. Neptune, 1.64 grams per cubic centimetre. Neptune's density tells you immediately that it is a different kind of giant, enriched in heavier ices and molecules beyond hydrogen and helium. Neptune has a more substantial interior, probably including water, ammonia and methane ices, in a compressed, perhaps slushy or ionic state. Even Neptune, which is in some ways the odd one out among the gas giants, is 27 times denser than WASP-193b. Earth, 5.5 grams per cubic centimetre. Our planet's density reflects its iron core and rocky mantle, solid, compressed minerals and metals. Earth is about 93 times denser than WASP-193b. From WASP-193b's perspective, Earth would be an almost absurdly dense object. A main sequence star like our Sun, approximately 1.4 grams per cubic centimetre on average, though the core reaches thousands of times that at its centre where fusion occurs. The average density of the Sun is actually not far from Neptune's, and not wildly different from Saturn's or Jupiter's, which is part of why the boundary between very massive planets and small stars is a blurry one, defined more by whether nuclear fusion is occurring than by dramatic differences in average density. Interstellar medium, the extremely tenuous gas between stars, roughly 10 to the power of minus 24 grams per cubic centimetre, an atom or two per cubic centimetre. WASP-193b is vastly denser than this, of course. It is still a coherent planetary body, not a wisp of gas, but the comparison helps calibrate just where on the density spectrum it sits. Aerogel, one of the least dense solid materials ever made, around 0.001 grams per cubic centimetre for extremely lightweight versions. WASP-193b is actually denser than aerogel, which should be reassuring in some sense. It is not trying to outcompete human engineering in lightness, but aerogel is a material so lacking in substance that you can see through it, that it transmits weight almost without any apparent response, that it seems to exist primarily to surprise people at science demonstrations. The fact that WASP-193b sits within an order of magnitude of aerogel in density, while being a planet, says something. And one more comparison, perhaps the most affecting: a soap bubble. The thin liquid film of a soap bubble has a density roughly comparable to water, about 1 gram per cubic centimetre. But a soap bubble as a whole object, sphere plus interior air, has an average density far lower than WASP-193b. In that sense, a soap bubble is less planet-like in its density than WASP-193b is. The cotton candy planet, for all its lightness, is at least denser than a soap bubble. These comparisons are not just curious diversions, they situate WASP-193b on the scale of physical reality and help us understand what we are actually claiming when we say it is extraordinarily light. It is not lighter than everything we know, but it is lighter than anything we have previously confirmed as a planet. One aspect of WASP-193b's existence that deserves deeper exploration is its likely tidal locking. When a planet orbits its star closely enough and for long enough, the tidal forces from the star gradually slow the planet's rotation until one face permanently points toward the star. The time required for this to happen depends on the planet's properties and its distance from the star. But for a hot Jupiter at WASP-193b's orbital distance, tidal locking is expected to occur relatively quickly by astronomical standards, within hundreds of millions of years, perhaps faster. WASP-193b has been orbiting its star for what is probably billions of years. Its star is not a newborn. It is an established F-type star on the main sequence, suggesting an age of at least several billion years. At these timescales, WASP-193b has almost certainly been tidally locked for most of its existence. It presents one face to its star forever. What does this mean for the planet's atmosphere and climate? The day side, permanently facing the star, receives an unrelenting bombardment of stellar radiation. This half of the planet is hot, very hot. Estimates of the equilibrium temperature suggest it could be over 1000 Kelvin on average, but the substellar point, the spot directly under the star, the noon of an eternal day, could be considerably hotter. The extreme irradiation drives intense photochemistry in the upper atmosphere, breaking molecules apart and generating exotic chemical products. The night side, by contrast, receives no direct stellar radiation. It is cold relative to the day side, though not as cold as it might be if the atmosphere were thin and transparent, because atmospheric circulation carries heat from the day side to the night side. Hot Jupiters are known to have dramatic temperature contrast between their two hemispheres, though the degree of contrast varies based on how efficiently their atmospheres transport heat. For WASP-193b, the atmospheric heat transport is a particularly interesting question. The planet's low density implies a very extended diffuse atmosphere, one in which winds might behave differently than in a more compact gas giant. The circulation patterns driven by the temperature contrast between the permanent day and permanent night sides could be spectacular in their scale and intensity. The jet streams and wind patterns in WASP-193b's atmosphere, if we could somehow observe them directly, might be unlike anything in our solar system. This asymmetric heating also has implications for atmospheric escape. The day side, being hotter and more intensely irradiated, experiences the most intense photoevaporation. The upper atmosphere on the day side is heated to higher temperatures, and gas is more likely to achieve escape velocity on that side. Mass loss from tidally locked hot Jupiters tends to be enhanced on the day side, creating a symmetric outflow that some models predict could produce detectable signatures, a tail of gas flowing away from the planet in the orbital direction, detectable in transit observations as an asymmetry in the light curve. For WASP-193b, if mass loss is occurring at a significant rate, this asymmetric outflow might be one of the observable signatures that future observations could detect. It would manifest as a subtle asymmetry in the transit shape, the ingress and egress of the transit not being perfectly symmetric, or as an excess absorption in certain spectral lines, indicating the presence of gas extending beyond the planet's atmosphere proper. Tidal locking, in short, is not just a geometric curiosity. It shapes the planet's atmospheric dynamics, its chemical evolution, its pattern of mass loss, and potentially the observational signatures we might use to characterize it. WASP-193b is a world of two eternal faces, one burning, one frozen, both carrying information about the planet's nature, and the boundary between them, the terminator region, where day perpetually meets night, may host some of the most dramatic weather in the planetary system. It is tempting in a documentary about WASP-193b to treat the star as merely a backdrop, the light source, the gravitational anchor, the energy provider. But WASP-193 is not passive in this story. It is an active participant, perhaps the key factor driving what makes its planet so extreme. F-type stars occupy an interesting position in stellar physics. They're not hot enough to produce the extremely intense X-ray and ultraviolet radiation that early type stars like A or B types generate, but they are notably more energetic in those wavelengths than cooler G or K-type stars. An F-type star's high energy output, the ultraviolet and X-ray photons that drive atmospheric escape, is significantly greater than our Sun's. This means that WASP-193b, orbiting an F-type star at extremely close range, yet is bathed in a particularly intense flux of planet-stripping radiation. The combination of closeness and the star's inherent energetic output creates conditions at the upper end of what any giant planet could be expected to endure over billions of years while remaining as inflated as it is. This raises a question that is worth sitting with. Has WASP-193b always been this large? Or was it once even larger, and we are seeing it in a state where it has already lost a significant fraction of its original atmosphere? If the planet formed even more inflated, if its initial density after formation was even lower than what we measure today, and has since been steadily losing mass through photoevaporation, then the current state is not the original state but a contracted version of it. The planet we measure today, strange as it is, might be a depleted remnant of something even stranger that existed 1 billion years ago. This is speculative, but it is physically plausible. The timescale for significant mass loss in an extreme irradiation environment can be comparable to stellar main sequence lifetimes. A planet that formed in the right conditions and migrated to a close orbit early in the system's history could have been losing mass for billions of years by now. What we measure today might be the current snapshot of an ongoing process. Alternatively, if the planet originally formed with a more typical gas giant density and has been inflated by stellar irradiation, if irradiation-driven reinflation has been operating continuously or recently, then the current state is more inflated than the original. The planet is growing, not shrinking. The two scenarios, ongoing deflation through mass loss versus ongoing inflation through irradiation, could in principle be distinguished through careful atmospheric observations and mass loss rate estimates. And here, again, is where observations become absolutely essential. Theoretical arguments can construct both scenarios as plausible. Only observations of the actual atmosphere, its composition, its structure, the rate at which material is escaping, can break the degeneracy and tell us which direction the planet is travelling. The star WASP-193 does not merely illuminate this story, it is actively writing part of it every moment as its radiation pours over the planet and shapes whatever is happening in that extended, diffuse, implausibly light atmosphere. WASP-193b does not exist as an isolated puzzle. It is one piece in a larger mosaic of unsolved problems in exoplanet science that are, in various ways, interconnected. Consider the radius gap, a feature in the exoplanet size distribution discovered through statistical analysis of Kepler data. When you plot the distribution of exoplanet radii, you find that there are many planets smaller than about 1.5 Earth radii, many planets larger than about 2 Earth radii, and surprisingly few planets in between. This gap in the distribution has been interpreted as evidence of atmospheric escape operating efficiently in that size range. Planets that start with modest gas envelopes lose them entirely to photoevaporation over time, leaving behind bare rocky cores, while planets that are more massive retain their envelopes and remain at larger sizes. The atmospheric escape, the same process we discussed in the context of WASP-193b, is therefore not just relevant to extreme cotton candy planets. It is a population-level sculpting force that shapes the size distribution of all exoplanets. The efficiency with which planets lose or retain their atmospheres depends on the same physical parameters that govern WASP-193b's precarious situation: stellar radiation intensity, planetary gravity, atmospheric composition and structure. Superpuffs like WASP-193b sit at the extreme end of this continuum. They are the planets where atmospheric retention is most difficult, where the gravitational binding is weakest, where escape is most likely to be ongoing and significant. They are, in a sense, the leading edge of planetary evolution, the worlds that will change most dramatically over time, that are currently in transition from their formation states toward whatever eventual equilibrium they settle into. The desert of short-period Neptunes is another parallel puzzle. Observations suggest that there are very few planets in the size range of Neptune, several times Earth's mass, with orbital periods shorter than a few days. This hot Neptune desert is thought to be the result of photoevaporation stripping the envelopes of Neptune-sized planets that form or migrate close to their stars, leaving behind either bare cores or nothing. But hot Jupiters, being more massive and therefore better able to retain their atmospheres against photoevaporation, do survive at short periods. They are the hot Jupiters. WASP-193b is a hot Jupiter, sort of. Its mass is more similar to Saturn than to Jupiter, and its density is below anything in the hot Jupiter population, and suggesting that it is perhaps not as well buffered against photoevaporation as a typical hot Jupiter. It occupies an interesting niche, massive enough not to have been completely destroyed by its proximity to the star, but light enough that its long-term fate is far from secure. Understanding how WASP-193b fits into these broader population-level patterns, the radius gap, the hot Neptune desert, the superpuff problem, is part of why it is scientifically valuable beyond just being intrinsically astonishing. It is a data point in a larger story about what happens to planets at the extreme end of the parameter space, and how the universe differentiates between planets that survive their stellar environments and those that are eventually consumed by them. The James Webb Space Telescope, JWST, has been mentioned in this documentary several times, but it deserves a fuller accounting of what it represents and why it matters specifically for a world like WASP-193b. JWST represents the culmination of decades of planning, engineering, and international collaboration. It is not just a bigger Hubble, it is a fundamentally different instrument operating in different wavelengths, with capabilities that were designed from the ground up to answer questions that Hubble simply could not. The telescope's primary mirror is 6.5 meters across, about 2.7 times the diameter of Hubble's primary mirror. But the dramatic difference in area, about 6.25 times more collecting area, is only part of the story. JWST observes primarily in infrared wavelengths, from near-infrared through mid-infrared. This is the range where the thermal emission from exoplanet atmospheres peaks, where molecules like water, methane, carbon dioxide, and dozens of others have their most diagnostic spectral features, and where the atmospheric chemistry of distant worlds can be read most clearly. JWST carries 4 scientific instruments, 2 of which are particularly relevant for exoplanet atmospheric science: NIR-SAG, the near-infrared spectrograph, and MIRI, the mid-infrared instrument. NIR-SPEC can take spectra of transiting exoplanets with extraordinary sensitivity, detecting molecular features that would be far below the detection threshold of previous instruments. MIRI extends the wavelength coverage into the mid-infrared, where additional molecular features and thermal emission signatures can be measured. For WASP-193b, JWST represents the possibility of going from a density measurement, an indirect clue to the planet's nature, to actual direct evidence about what the planet's atmosphere contains. A transmission spectrum from JWST would tell us what molecules are present in the atmosphere at the altitudes that the transit light passes through. It would constrain the atmospheric temperature structure. It might detect the signatures of escaping gas. And by comparing the detailed spectrum to theoretical models, it would help discriminate between different hypotheses about the planet's formation and evolution. The planet is a particularly favourable target for JWST because of its inflated atmosphere. As mentioned earlier, an extended atmosphere produces a stronger transmission signal because there is simply more atmosphere for the starlight to pass through at the edge of the disk. For superpuff planets, this translates into transmission spectra that are more easily measurable than for compact planets of similar masses. WASP-193b's very strangeness, the property that makes it scientifically puzzling, also makes it scientifically accessible. There is, however, a possible complication. Some superpuff planets observed with previous telescopes have shown unexpectedly flat transmission spectra with fewer strong molecular features than models predict. The leading explanation for this is that high-altitude clouds or hazes in the upper atmosphere can obscure the molecular signatures from below, making the spectrum appear featureless. If WASP-193b has a thick haze layer in its upper atmosphere, plausible given the intense irradiation and active photochemistry expected in this kind of environment, JWST might find a more challenging spectrum than models naively predict. But even a flat or hazy spectrum would be informative. It would tell us that the upper atmosphere is dominated by haze-forming chemistry, constrain the particle sizes and optical properties of the haze, and set limits on the atmospheric metallicity. JWST's mid-infrared capabilities might be able to see below cloud decks that are opaque in the near-infrared, because the cloud and haze materials that are opaque at shorter wavelengths may become more transparent at longer ones. The bottom line is that JWST has opened a new era of exoplanet atmospheric science, and WASP-193b is one of the targets that this era was built to study. The answers that JWST can provide, whether they reveal a hydrogen-helium-dominated atmosphere, exotic chemistry, escaping gas, or something unanticipated, will be pivotal for understanding why this planet exists and what its future holds. There is a particular moment in the story of any scientific discovery that does not often get told. It is the moment before the paper is published, before the press release goes out, before the world knows. It is the moment when a researcher or a team is sitting with data that they have checked and rechecked, that they know is real, that they know is strange, and that they are preparing to share with the rest of the scientific community. What is that moment like for something like WASP-193b? The discovery team, Khalid Barkawi and collaborators, were working with data from the WASP survey and from follow-up observations taken with spectrographs on professional ground-based telescopes. The transit signal had been flagged, the follow-up photometry had confirmed the planet's size, and then the radial velocity data came in, and the mass was small, much smaller than the size implied it should be. The density calculation was run, and the number came out somewhere in the neighbourhood of 0.06 grams per cubic centimetre. In a moment like that, the first reaction is probably doubt. Was there an error in the stellar radius estimate? Could the transit signal be a false positive, a background eclipsing binary star contaminating the signal, making the dip look bigger than it is, making the planet look larger than it is? Were the radial velocity measurements affected by stellar activity in a way that underestimated the true mass? All of these are legitimate concerns that would be carefully checked, but the checks came back. The stellar radius estimate was robust based on spectroscopic analysis of the star's properties. The radial velocity signal was confirmed across multiple epochs and instruments. The transit signal was well measured and self-consistent. The planet was real. The density was real. This is the moment when doubt transitions into something else. Something that sits between excitement and discomfort. Excitement because this is extraordinary. Discomfort because extraordinary results demand extraordinary justification, and extraordinary results that do not fit existing models invite scrutiny. In the scientific community, announcing something truly anomalous is not a simple act of sharing information. It is an invitation for others to examine your methodology and argue with your conclusions. The scrutiny is valuable. It is how science works. The discovery of WASP-193b was not accepted simply because someone said so. It was accepted because the data was examined, the analysis was reviewed, and the result held up. The density of this planet is not a measurement artifact. It is a real property of a real world. But knowing that does not fully dispel the strangeness of the moment when you realize that you have found something that genuinely challenges what we know. That is a rare moment in science, and it deserves recognition as such. Most scientific work, even excellent scientific work, confirms and extends existing knowledge rather than challenging it. The occasions when the data says, your framework is incomplete, those are the occasions that live longest in the history of any field. To fully appreciate what WASP-193b represents, it helps to zoom out and see the larger arc of the story we've been telling for centuries about planets. For most of human history, the word planet referred to the wandering lights in the sky. the objects that moved against the fixed background of stars. 5 were known in antiquity: Mercury, Venus, Mars, Jupiter, and Saturn. They were mysterious, divine, important for navigation and timekeeping. Their natures were unknown. The scientific revolution of the 17th century transformed this. Telescopes revealed the planets as real physical objects: Jupiter with its moons, Saturn with its rings, Venus going through phases like the Moon. Newton's laws of motion and universal gravitation gave a mathematical framework for understanding planetary orbits. The planets became objects subject to physics, not to mythology. Over the following centuries, the solar system was mapped in increasing detail. The outer planets, Uranus and Neptune, were discovered. The moons of the gas giants were characterized. Spectroscopy allowed astronomers to measure the composition of planetary atmospheres from Earth. Space missions starting in the mid-20th century provided close-up views of the planets and transformed our understanding from broad strokes to intricate detail. And then, in 1995, the exoplanet era began in earnest. Suddenly the word planet expanded from referring to 8 objects in our solar system to referring to a catalogue that now numbers in the thousands, and will eventually number in potentially hundreds of thousands. Yet the question, what are planets, went from being a solar system question, answered by looking at our own neighbourhood, to a galactic question, requiring observations across thousands of light years. This expansion of the concept of planet has been humbling and thrilling in roughly equal measure. Humbling because it revealed how limited our sample had been. 8 planets is not enough to generalize to the galaxy, and we were right to worry about that. Thrilling because the galaxy turns out to contain an almost inexhaustible variety of worlds. WASP-193b is a product of this expansion. Without the transit surveys, without the radial velocity spectrographs, without the decades of methodological development that made exoplanet detection routine, we would never have known it existed. It would have continued orbiting its distant star, going through its 6.25-day year, completely unnoticed by any intelligent being in the universe. The fact that we found it is a tribute to human ingenuity, patience, and the willingness to build instruments designed to detect signals of extraordinary subtlety from sources at extraordinary distances. The WASP survey was not designed specifically to find WASP-193b. It was designed to find lots of planets by monitoring lots of stars, and WASP-193b was among the planets that revealed themselves to that careful, patient watching. In a sense, the discovery of WASP-193b is the outcome of a long arc that begins with Galileo pointing a lens at Jupiter and seeing its moons, and runs through 2 centuries of solar system science, and then through the exoplanet revolution, and arrives, here, now, with this improbably light planet, at a place where the science is still actively being constructed. There is a tendency, when we describe the natural world, to present it as more orderly than it actually is. We learn about the solar system and it seems clean, comprehensible, almost designed. The rocky planets close in, the gas giants far out, the ice giants at the edge. We learn about stellar types and the sequence seems logical. We learn about galaxy formation and the narrative flows. But the deeper you look, the more you see that the universe is not orderly in the way a textbook implies. It is orderly in the sense that physics governs everything. There are laws, there are constraints, there are outcomes that are more likely than others. But within those constraints, the universe explores an enormous space of possibilities. And some of those possibilities are things that, when we encounter them, it does make us say, this should not exist. WASP-193b is one of those things. It should not exist. Not in the sense that it breaks the laws of physics. It does not. Gravity still works. Radiation still drives atmospheric heating. Gas still obeys the equations of state. The planet is not magic. It is physics, applied to a specific set of initial conditions and allowed to evolve over billions of years. But it should not exist in the sense that the initial conditions that produced it and the evolutionary history that brought it to its current state are apparently so unusual that our standard models of planetary formation and evolution did not predict it. We built those models based on the planets we could see, and we thought those planets were representative of what the universe produces. WASP-193b is telling us that we were wrong about the full extent of what is possible. This is not a failure of science. It is science in its most productive state, encountering the unexpected, updating its models, expanding its understanding. Every anomaly in the history of science that was taken seriously and followed to its conclusion has deepened human understanding. The anomaly of Mercury's orbital precession, unexplained by Newtonian gravity, pointed to general relativity. The anomaly of galaxy rotation curves pointed to dark matter. The anomaly of the accelerating cosmic expansion pointed to dark energy. These are not minor footnotes. They are among the most important scientific discoveries of the last century. WASP-193b is probably not pointing at dark matter or a new fundamental force, but it is pointing at something. A gap in our understanding of planetary physics, a regime of mass and radius and irradiation that our models have not properly captured. And when we close that gap, when the combination of better observations, particularly from JWST, and better theoretical models, finally gives us a framework that explains not just WASP-193b but the entire spectrum of superpuff planets, we will have learned something real and important about how planets work. Every scientific discovery poses more questions than it answers. This is sometimes said as a truism, a pleasant sentiment about the endless frontier of knowledge. But in the case of WASP-193b, it is specifically, concretely true in ways worth enumerating. What is the planet's atmospheric composition? We do not know. Transmission spectroscopy with JWST or similar instruments is needed. Is it currently losing mass? We believe it probably is, based on theoretical considerations, but we have no direct observational measurement of the mass loss rate. What is its interior structure? We have inferred from the density that it probably lacks a massive solid core, but we cannot directly probe the interior of a planet 1,200 light-years away with current technology. How did it form? We have multiple hypotheses: core accretion under unusual conditions, disk instability, migration history, but none of them is decisively supported over the others by current data. Is it representative of a class of planets, or is it an extreme outlier even among superpuffs? The answer matters for understanding how common these worlds are and how they fit into the broader landscape of planetary evolution. What will it become? If mass loss is ongoing, how quickly is it losing atmosphere? And will it eventually transition into a smaller, denser object, a bare core or a sub-Saturn? Or will the reinflation driven by its aging, brightening star keep pace with the mass loss and maintain the inflated state for billions of years to come? Does it have moons? Any ring system? These are probably not detectable with current instruments for a planet this distant, but they would matter for understanding the planet's dynamical history. Each of these questions represents a research program, potentially years of telescope time, theoretical development, and careful analysis. Some of them may be answerable within a decade, given the capabilities of JWST and the next generation of ground-based, extremely large telescopes. Others may require technology that has not yet been built. The questions that outlast the initial discovery are not signs of failure. They're signs that WASP-193b is a rich enough object to keep giving. It is the kind of discovery that launches careers and motivates the construction of instruments and invites a generation of researchers to engage with its mysteries. In the long run, the planets that are hardest to explain are the ones that most expand our understanding when they finally yield their secrets. The easy planets, the ones that fit neatly into existing categories from the moment of their detection, confirm what we already know. The hard ones push us further. There is a final dimension to WASP-193b's significance that goes beyond the purely scientific, and it has to do with what this planet represents in a broader sense for how we understand the universe and our place in it. We've always used the planets as mirrors. When we look at Mars, we see a world where something went wrong, where the atmosphere thinned and the water disappeared and the surface became a cold desert. We ask, could that have been us? When we look at Venus, we see a world where something also went wrong in a different way, where a runaway greenhouse effect turned a potentially hospitable world into a hellish cauldron. We ask, could that be our future? When we look at the gas giants of our own solar system, we see objects utterly unlike Earth. Worlds that are not places in the conventional sense, but vast volumes of gas sustained by their own gravity, with no surfaces to stand on and no biospheres to complicate their physics. They are the universe practicing planetary science in its purest form, without life to complicate the picture. And when we look at WASP-193b, this extraordinary, improbable cotton candy world, what do we see? We see the universe operating at the very edge of what gravity can sustain. We see a planet that is so lightly bound that it exists in a constant conversation with the radiation from its star, a negotiation over whether it will remain a coherent object or slowly disperse into the void. We see a reminder that the range of things that can exist under the laws of physics is wider than our experience of a single solar system suggested. There is something humbling about this. We've spent centuries building mental models of what planets are, and WASP-193b arrives to tell us that our models were too small. Not wrong, the physics is the same everywhere, but the range of outcomes that the same physics can produce, the variety of configurations it can create and sustain across the galaxy, is larger than we had appreciated. The universe does not consult our categories before making planets. It does not check whether a particular configuration fits our theoretical frameworks before allowing it to form. It simply applies the same fundamental laws everywhere, allows initial conditions to vary, permits evolution to play out over billions of years, and produces whatever it produces. Sometimes that is Earth, sometimes it is Jupiter, sometimes it is a planet so light and so vast that the most accurate single-word description we have for it is cotton candy. And we sit here on our dense, heavy, life-giving rock with our telescopes and our spectrographs and our equations, and we try to understand what we are seeing, not because it affects us. WASP-193b is 1,200 light-years away and is utterly indifferent to our curiosity, but because understanding is what we do. Because knowledge of the universe's range is knowledge about what the laws of physics permit, and the laws of physics are the same laws that govern us. WASP-193b does not threaten us. It does not beckon us. It is not habitable, not visitable, not relevant to our daily lives in any direct sense. But it exists, which means the universe contains it, which means our understanding of the universe must make room for it. And making room for it means rethinking, expanding, revising the models and the intuitions that we built before we knew it was there. We live in an extraordinary moment in the history of planetary science. 10,000 exoplanets confirmed, thousands more candidates waiting for follow-up, surveys scanning millions of stars simultaneously, spectrographs achieving radial velocity precisions of less than a meter per second, a space telescope orbiting 1,000,000 miles from Earth, gathering infrared light from objects half a galaxy away, reading the chemical fingerprints in the atmospheres of worlds we will never visit. And yet, we find things we cannot explain, still, routinely. The more data we gather, the more mysteries we uncover, because the universe is richer than any model we have built. Not infinitely richer, not beyond comprehension in principle, but always one step ahead of our best understanding. WASP-193b sits at that one step ahead position right now. It is not the last planet that will surprise us. There will be other super puffs, other density outliers, other objects that make astronomers reach for their calculators and double-check their results, and eventually accept that yes, this is real, and no, we cannot yet fully explain it. The catalogue of exoplanets is young. The era of detailed atmospheric characterization is just beginning. The next decade will almost certainly deliver objects more surprising than WASP-193b, and they will push the models further, and the models will respond by growing larger and richer and more capable. But WASP-193b is here now. It is the edge that we have found so far, and there is something valuable about knowing exactly where the edge is. In standing at the boundary of the known and looking at the specific, particular thing that marks it. The edge is not a wall, it is not a warning sign, it is an invitation, 1,200 light-years from where you're sitting. Orbiting a star slightly hotter than our own, in the quiet of intergalactic time, a planet the size of Jupiter, larger than Jupiter, completes one full year in the time it takes you to live through 6 days. It has no surface in any meaningful sense, no solid ground, no liquid ocean, nothing to land on, just gas and more gas, gradually compressed but never into anything we would recognize as solid, perhaps all the way down to whatever diffuse center it might possess. An atmosphere that begins nowhere in particular and ends nowhere in particular, that extends upward for thousands of kilometers because the gravity pulling it down is far too gentle for something this large. It is bathed in the light of its parent star, always on one face. The other face is in permanent darkness, cold by comparison, but not cold by any measure that would make sense to us. The winds in that atmosphere blow at hundreds of kilometers per hour, probably, carrying heat from the searing day side around to the shadowed night side in a constant, ancient circulation that has not ceased since the planet formed, and it is being consumed, probably, slowly, by stellar standards, which is to say, quickly, by planetary standards. The radiation from the nearby star is eroding the outer layers of the atmosphere, lifting gas away from the planet and sending it spiraling out into space, lost forever. The planet is exhaling, very gently, and has perhaps been exhaling for billions of years. what it will look like in another billion years, smaller, more compact, as a reformed world bearing little resemblance to the cotton candy sphere we observe today, we cannot say with certainty. It depends on the race between inflation and evaporation, between the energy driving the atmosphere outward and the mass loss carrying it away. We know it exists, we know its density, we know it should not be as light as it is, and we know that we do not yet fully understand why it is. That is enough. That is actually more than enough, more than previous generations had any right to expect from a star 1,200 light-years away, more than was possible with the technology of even 20 years ago. We know a world is out there, enormous and almost weightless, orbiting its scorching sun in its short year, dissolving slightly into the radiation, holding together under the barely sufficient grip of its own gravity. We know all of this, and we do not yet know why. And in that gap between knowing it exists and knowing why it exists, there is the whole future of a science that is still, even now, in its early chapters. The complete story of WASP-193b has not been written. The observations that will determine its atmospheric composition are either planned or already underway. The theoretical models that will finally explain its density are, perhaps, in the hands of a graduate student somewhere, being written and revised and tested against this remarkable datum that nature has provided. The universe is not waiting to be understood. It does not need our understanding to continue doing what it does, forming planets, shining stars, running physics experiments at a scale we cannot replicate and can barely observe. The cotton candy planet will orbit its sun regardless of whether we understand it. The gas will continue to stretch and thin and drift away into space regardless of whether our models can explain it. Time will pass in quantities that dwarf any human measurement, and the planet will evolve. And the star will evolve, and eventually something will end. The planet will disappear, the star will die, and the system will become something else entirely. But right now, in this window of time that happens to coincide with the existence of humans, with telescopes and mathematics, and a compulsive need to understand things, we can see it, we can measure it, we can wonder at it and argue about it, and propose explanations for it. We can recognize that it is one of the strangest confirmed objects in the known universe, and we can remember, each time we look at it, that the universe is under no obligation to be comprehensible to us, that physics is vast enough to permit things we did not expect, that the laws we discover are not limits on what can exist, but descriptions of how everything that does exist behaves, and that somewhere in the space of what those laws permit, there is a planet that should not be, and is. There it sits, WASP-193b, cotton candy in the void, the universe's reminder that we still have questions.